Hello everyone, in this video I wanted to discuss an interesting method on how to approximate pi using nested radicals of 2. It's a method I actually found out about years ago when I was just trying to do approximations of pi using areas of circles. In fact, really, if you consider a circle, let's draw one here, of radius 1, then you can say that the area of that circle, of course, is just pi itself. Which makes a ton of sense because, of course, area of a circle is pi times the radius squared. And then, of course, since the radius is 1, pi times 1 squared is just pi. So if we can approximate the area of the circle, then we can approximate pi. So that's the idea there. And actually, if you started off by inscribing shapes inside of circles, that was kind of my first idea. And by the way, this isn't something I groundbreakingly discovered or anything like that. This has actually been done before. I did some research, and actually the formula that I came up with, which I'll share with you in a bit once we come to kind of the end of this, I found out after doing a little bit of research that someone has already come up with this formula. But I don't know how well known it is because it took a lot of digging to find it. Anyways, let's say the center is about right here, right? So I'm inscribing a square inside of a circle. Now the first question you have is, what is the radius of this circle? Or not radius, but what is the side length of this square? So what's the side length of this square? Well, since each of these lines I just drew are radii of the circle, the radius of the circle, the radius is 1. So by Pythagorean theorem, since this angle is 90 degrees, this has to be the square root of 2. Now, of course, we know it's 90 degrees because we're splitting it into kind of 4 sides, right? So this angle of 360 degrees is divided by 4, and 360 divided by 4 is 90. So that's how I know that. Okay. Now, if you find the area of this square, I'll call this A1, and this is going to be radical 2 squared, which is just 2. Okay. Now, 2 is way less than pi. Right? We know what we're aiming for. Pi is 3.14 or something. So what we're going to do now is we're going to ditch the square, and from the square actually create kind of shape that's closer to a circle. So what I'm going to do is I'm actually going to find the midpoint of the side and create a line from the circle through that midpoint until I touch the circle. From the center of the circle to the end of the circle, passing through the midpoint of the side length of the square there. Now, of course, you can connect these points here and here, also here and here, and you can do that all the way around, and you'll end up getting an octagon, actually. Now, it's worth noting, remember that the side length of the square was radical 2, so this base of this triangle we get here is radical 2 over 2. So I'll actually show you by drawing it what the octagon more or less looks like, because it's kind of interesting to see. Okay. I don't trust me doing the lines hand-free like that. But there we go, that's the octagon. Fantastic. And you can ditch the square so you can see what it looks like. Pretty cool. Now, the area of the octagon isn't nearly going to be as close as pi as we want it to be, but it's much closer than the previous area, which was 2. So let's see if we can figure it out. Now, the way I did this was, well, think about it. We have these 4 new triangles, right, which I'll highlight here in yellow. So what you can say is that this new area, which I'll call A2, is just the previous area plus 4 new triangles. So I'll say A2 is A1 plus 4 new triangles. The area of these 2 triangles here. Now the area of one triangle is actually just, so let's kind of ditch this highlighting for a bit. So the area of this one triangle, of the top triangle, is really 2 times this highlighted area here. And you can see the height of this, if we call this height x, then we can see that this is really, area of the triangle is literally equal to x times the square root of 2. And you may think, well, area of a triangle is 1/2 base times height, and that's true, but 2 of those highlighted triangles make that one triangle we're trying to find. So notice this is half of the triangle already. So that already includes the half, basically. Because the base of the entire triangle is just radical 2, and 1/2 of that makes this radical 2 over 2. So I hope that makes sense. Now, what is x then? Well, if you draw a line from here to here, kind of what we had from the square already, notice this will be 90 degrees because of it being a line that passes through the midpoint. Basically, it's a perpendicular bisector. And because it's the radius of the circle, that line there, the hypotenuse of this new triangle we've created, is 1. We can actually find this length by Pythagorean theorem, and it's going to be 1 squared minus radical 2 over 2 squared, which notice radical 2 over 2 squared is 2 over 4, which is 1/2. And also, well, 1 squared is 1, and 1 minus 1/2 is 1/2. Now, because of Pythagorean theorem, we really get the square root of this, which of course is radical 2 over 2 still, which is not too surprising because radical 2 over 2 is really radical, it's 1 over radical 2. So in fact, this new white triangle we have is really just, I guess, a factored down version or a scaled down version of a quarter of the square we saw earlier. So it's kind of interesting. In fact, you can see multiplying everything by radical 2 gives you a 1, 1 radical 2 triangle. But anyways, what does it tell us about x? Well, notice this entire, let me highlight it here, this entire length is a radius, so it's 1. So that means x, we know, must be what? It must be 1 minus radical 2 over 2. So that means this is 1 minus radical 2 over 2 times the quantity radical 2 over 2. Great. So distribute that. We get radical 2 over 2 minus radical 2 times, well, radical 2 over 2 multiplied by itself is 2 over 4, which is 1/2. So we end up getting that for the area of this triangle. Okay. So I'm going to simplify this a bit because we know what A1 is and we can distribute that 4 as well. Notice A1 is 2, and distributing that 4 gives us 2 radical 2 minus 2, and look at that, the 2's cancel and we get 2 radical 2. And that is the area of this octagon, but again, nowhere near close to pi. In fact, I think this is about 2.8. You can check these approximations on your own. But there we go, that's the area of the octagon, that's A2. Now we're going to do, what do you think? We're going to extend this even further into a 16-sided polygon, otherwise known as a 16gon. Now to do that, we're going to have to zoom in on one of these triangular sectors and basically create a new perpendicular bisector from which we'll be making our new sides, one there and one there. It's really tiny to see, to zoom in really hard to see that. In fact, this new polygon will have an area even closer to pi, but still not quite close enough. It's going to be like 3 point, maybe 1. I think it's 3.0 actually. I'm not quite too sure. I forget the exact values. But it doesn't matter. The point is we're getting closer and closer to pi. Now, what do you think the area will be? What is A3? Well, it's the previous area, which is the area of the octagon, A2, plus 8 new triangles. Notice we have one triangle here. We'll have one triangle here, 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 and here. One for each of the previous side, which was, there were 8 of them, right? So I hope that makes sense. Okay, so now the question is, how do we find the area of that triangle? Now that requires a lot of work and a lot of patience. Let's do it though. Let's see. In fact, let me kind of, I don't want to, I mean, I could get rid of the picture, I guess, but I don't want to get rid of the picture. So instead, I'm going to kind of move to the side and try to create this picture zoomed in a bit. So let's see if we can do that. So we have this triangular sector, imagine. Something like that. And we bisected it. I guess I'll show that in blue. Okay, not to scale, but there we go. You get the idea. And we have these new side lines, which I guess I'll draw in red, here and here. So these are the side lines of our 16gon. Again, not to scale, doesn't look exact, but there we go. That's the idea. So what do we know? Well, we actually know a few things, but we need to look at the previous picture to come up with some of these ideas. So what we don't know is actually the base of that triangle. That's what we're trying to find. That's one of the things we need to find, is the base of the triangle and also the height of this triangle. If we find the base and the height, then we have the area of the triangle, and we're kind of done. To find the base, though, notice if you look back at the original octagon, well, where that side length came from is from a triangle that looks something like this. This is what it looks like when I draw things freehand. Not too bad, I guess. So remember, that was x, which we found out was just 1 minus radical 2 over 2. That was x. Luckily, I kept that. And the base was radical 2 over 2. Now the question is, how do we find the hypotenuse of this triangle? Of course, Pythagorean theorem. So if I call this C, maybe we don't need to be that detailed, but we know it's a square root of the sum of the squares of the other sides, right? Now, if you square radical 2 over 2, we know that's 1/2, plus this, if you square the other thing, you get this, that quantity squared. Now, if you actually square that quantity, you'll have the first one squared, 2 times the product, which is negative radical 2, and the last one squared is 1/2, which we kind of already did. Now look at this. These actually will all combine, which is really nice to see. What do they combine to is 2, because we have, of course, 1/2 plus 1/2 is 1, plus that other one is 2. So this ends up being radical 2 minus radical 2, like that. So we have a nested radical, kind of something I foreshadowed earlier. So that's the base of the triangle. What is the height of the triangle? Okay, again, a little tough, but the height of the triangle is 1 minus this part of the blue distance, which I'll highlight here in green. So how do we find that? Well, remember, this blue line is a perpendicular bisector, so we have a right triangle. Another right triangle. Great. So we know, I guess we can half, we can half that distance. So let's call this guy x, even though we already used x. So notice x is this distance we just found divided by 2. Well, I guess it's really double that. Right? Double x is the base of the triangle, which is the hypotenuse of the triangle I drew here. I know it's a little confusing, but there we go. Okay, so x is that over 2. So maybe we'll write that. X is this thing over 2. Perfect. So now we know this is the radius of a triangle, or radius of the circle, I meant to say, so it's 1. So we know that this green distance, which I'll call y, I guess, squared plus x squared is equal to 1 squared. So that means y, which we're trying to find, is a square root of 1 minus x squared. But x squared we can find by squaring the radical on top, which you just get the inside, and the bottom where you get 4. So it's 1 minus that quantity. So you kind of have to distribute the negative. In fact, if you split this fraction up, 2 over 4 is 1 over 2 minus radical 2 over 4. Distributing the negative, when you subtract, you'll get minus 1/2 plus the square root of 2 over 4. Notice 1 minus 1/2 is 1/2, so we get radical 1/2 plus radical 2 over 4. If you want to combine into one fraction, since 1/2 is 2 over 4, you get 2 plus radical 2 all over 4, and then taking square roots, you get radical 2 plus radical 2, radical 2 plus radical 2, nested radical, over the square root of 4, which is 2, which is almost like conjugate looking of x, so that's kind of interesting, actually. But what we're concerned with is finding the height of this triangle, which I should have used a different color, but that's okay, I guess. I'll use green, I suppose. This is 1 minus y. So y is this value, so we found 1 minus that. So again, a lot of work, and we need a lot of patience here, like I said. So we now have found that the area of the triangle that we're trying to find, remember that's 1/2 base times height, which really is just x times 1 minus y. Because x already is half the base, right? Now x we found out is the square root of 2 minus radical 2 all over 2, and 1 minus y is 1 minus this guy. Great, so now all we have to do is distribute, and we'll get the first quantity being just itself times 1, which is that, minus something all over 4. Now the great news is we have a radical times a radical, so it's just the product of the radicals inside of a radical. And even better, inside, multiplying those things, they're conjugates. So the question is, what is 2 minus radical 2 multiplied by its conjugate, 2 plus radical 2? Well, of course, by difference of squares, it's the first one squared minus the second one squared. 2 squared is 4, radical 2 squared is 2, so that's just 2 itself. So we get that. Okay, so let's put that above and let's see what happens. So this triangle, area of this triangle, we found is radical 2 minus radical 2 all over 2 minus radical 2 over 4. Great. So let's zoom in here and carry on with this calculation. So we know A2 is 2 radical 2. We know if we distribute the 8, well, 8 divided by 2 is 4, so it's 4 times this radical quantity, minus 8 divided by 4 is 2, and look at that, again we get a nice cancellation, so we get A3 is just equal to 4 times the square root of 2 minus radical 2. Now, this video is going to be very long if I even attempt to try to find A4. If you want to try A4, you can on your own. And, really, it's something I think I even went up to A5. It gets to the point where the calculation is really heavy. If you are very careful and pay attention, you can do it. But explaining as I go along, like I've done so far, it'll be a little much and really hard to follow, I think. But I really, really encourage you to do it. It's something I did, and it's a lot of fun. At least that's the right way to take it. It's all fun, okay? But I'll just tell you what you end up getting, just so you can check. So for A4, you'll get 8 times the square root of 2 minus the square root of 2 plus radical 2. That's what you'll end up getting. You'll get, very similarly, it's equal to A3 plus 16. You notice the amount of triangles doubles, of course, times the area of those triangles you end up getting, which will involve nested radicals. And when you distribute and combine, that previous A3 area will cancel out, just like A2 and A1 canceled in the previous calculations, and you'll end up getting this. A5 will give you 16 times the square root of 2 minus the square root of 2 plus the square root of 2 plus the square root of 2. Great. So, do you notice a pattern? Look at A1, A2, A3, A4, and A5. There is a pattern, and in fact, I probably should have labeled these a little differently. That's okay. I called it A1, A2, A3. I probably should have called these, I'm going to relabel things a bit. A0, A1, so that's A0. A2, so that's A1. A3, and A4. Why I just relabel it now is because you can maybe tell there's a common pattern with these numbers in front of the radicals. They're just powers of 2. Notice 16 is 8 to the 4th, and 16 is 2 to the 4th, and 8 is 2 to the 3rd. So I want to match the subscript here with those. So in fact, in general, there actually is a formula for A sub k. So A sub k, which is actually the area of the 2 to the k gone, or is it really the 2 to the k gone? Maybe not, because A3 was a 16 gone. So let me just write here and figure out what this actually is. This is the area of I guess it would be 2 to the k plus 1 polygon. 2 to the k plus 1 gone. Which makes sense because well, no, maybe not actually, because I keep taking it back. But this was that was a 2 to the 3 gone. That was an octagon. This guy, that was a 16 gone. That's a 32 gone. That's a, yeah. So it's plus. It's not plus 1. I'm sorry. It's k plus 2. My mistake. 2 to the k plus 2 gone. So the area is equal to this. It's equal to 2 to the, and again, this looks funny because it's 2 to the k, but it's a different k. So, well, actually, it's the same k. Well, k's aside, it's equal to 2 to the k times the square root of, let me make that line a little more straight, 2 minus the square root of 2 plus the square root of dot 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 plus, and it ends at radical 2. And how many 2's there are inside the radical is exactly k. K many 2's. In fact, it's the same as the amount of radicals, notice. So k many radicals. Now, something to notice, of course, is that they're not all pluses on the inside. The first one is a minus, and the next few, in fact, all of the other ones are pluses. There's not even alternating signs. So it's kind of curious. Now, can we actually verify this with a calculator? Sure, we definitely can. In fact, I actually posted a video for this on Pi Day, and I encourage you to watch the video where I used an iPhone calculator to do this. And it's actually much easier to do on a calculator like that, like an older style calculator, where you can just press plus 2 and then equals, and keep pressing equals, it keeps adding 2. Or you can press radical after, and it'll take square root of the previous number. Those older style calculators, this works great. And it's kind of interesting because older style calculators usually don't have a button for pi, where modern day scientific calculators do have a button for pi. So it's nice to know that it's kind of coincidentally, I guess, easier to use this method to approximate pi on the fly, which is pretty interesting. So that's the area of a 2 to the k plus 2 gon, where the I guess, radius of that polygon would be 1. So it's inscribed a circle of radius 1. But even, I think, more important for our purposes is, let me write this over here. This is like the big result. Is that if you take the limit as k goes to infinity, this is supposed to be exactly pi. Now, I haven't shown this rigorously at all. We just kind of played around with finding areas, and we saw that it's getting closer and closer and closer to a circle of radius 1, which has an area of pi. Great. So do you believe me? Well, again, you can use your calculator, and it works. It really does work. It's pretty amazing. When I found out about this, I was astonished, but then I researched it, and yeah, someone had done it already. But for some reason, I just hadn't heard about it until that point. So self-discovery is a really cool and interesting thing. But anytime you discover something, I would really recommend you do research, because chances are, unless it's really like niche or different, you weren't the first to think of that. There's so many people in the world, so you only figured that there, of course, would be someone before. But anyways, that just was the case here. But I did want to show you a proof rigorously of, well, at least more rigorously, of why this is true. And there is actually a way of doing that I found out about recently, which is one of the reasons why I wanted to show this, not just because of Pi Day, of course. So what we're going to start off with is this fact. And trying to think of exactly what, well, I'll just tell you what it is. So it's cosine of pi over 2 to the k, and this is equal to nested radicals of 2 added to itself, 2 added to previous radicals. Where the amount of radicals, or the amount of 2's, is not k, but k minus 1. K minus 1 many 2's. And by the way, I didn't include that description of that in the box, but I included the description of that before, so I guess it's okay. Maybe I'll just for closure, I'll write this, k many 2's. By the way, if you actually wanted to do this in the calculator, instead of remembering how many 2's to multiply by, because that's the thing, the only purpose of knowing how many 2's that are in your radical, or keeping track of how many 2's you had in the radical, was for this power. But a nice way around that is just multiplying that quantity you end up getting from that radical result by 2 a bunch of times until you hit pi. That's how I did it in the video anyways. So you start off with 2, take the square root, add 2, take the square root of that, add 2, take the square root of that. And you'll notice the values get closer and closer to 3 point, well, they get closer to 4, so it'll be 3.999. Then when you take the square root, they'll of course be closer to 2, it'll be 1.999 something. Then, once you're done with that, that's this part here. Then you need to do 2 minus that result, which is, I think I do like minus 2 and then take the opposite of that to make it positive. That's this. Then take the square root of that and then multiply that by 2 as many times as you have 2's in your radicals. Which of course, if you forget because you're not counting how many 2's you have, just multiply by 2. So press times 2 equals and press equals again. It'll keep doubling that result until you hit pi. So it's pretty cool to see it. So again, I recommend you try that on your own. Great. But now, how do we show this? So there's actually a way of showing this by induction. So there's a proof of this fact by induction. So induction, if you don't know, assumes that something is true up to a point, and then you show that it's true for the next value. When I say point, I really mean a positive integer value. So in fact, we'll use what is called a base case of, I guess we can do k to the, like k being 1, but then pi over 2, cosine of pi over 2 is 0, which I guess is kind of true because if k is 1, 1 minus 1, which is k minus 1, would be 0 many 2's, so there's no 2's. But really the base case I think we're concerned with is when k is equal to 2. So cosine of pi over 2 squared, notice that's cosine of pi over 4, which is radical 2 over 2. Aha! And that's the one thing I forgot. So we have to multiply this by 2 that many times. Right. I'm trying to think of a way of showing that. I guess we could... I guess we could multiply this by 2 to the k minus 1. You could also divide by 2 to the k minus 1 on the radical part. But again, I didn't really remember this result, which is why I'm kind of coming up with it a little bit on the fly. But this result is kind of used to prove this assertion, which we'll see in a bit. It's actually pretty interesting. But you need to have that connection of nested radicals with cosine like we have here. And the way to show it would be with induction. So we at least have a base case, which is nice. And notice multiplying by 2 gives you that. But again, an equivalent form would be cosine of pi over 2 to the k is that nested radical divided by 2 to the k minus 1. So 2 to the as many 2's as you have inside the radical. But it's all positive here, notice. Okay. So that's the base case. And now what we do is we suppose it's true for a value k. So suppose I hope you don't mind, but I'll write it in the other fraction form. That this is equal to the nested radical over 2 to the k minus 1, where you have k minus 1 many 2's inside. Okay, so this is for some integer k, some natural number k, some k in the set of natural numbers. Okay, so what I want to do now is I want to show that it's true for the next integer k. So if you can show that it's true for the next integer k, assuming that it's true up to some point, up to some integer k, then basically you can show that it's true for all integers. So that's the whole point of induction. So imagine we know it's true for 40. If we can show that it's true for 41, based on knowing that it's true for 40, then you can do the same to jump from 41 to 42, and you can continue that process and show that it's true for all values of k, basically. And this is called inductively. So this is what induction does that in general. So for k plus 1, what is cosine of pi over 2 to the k plus 1? So if you think about it, this is the same as cosine of pi over 2 to the k over 2. So in fact, really what we're going to do is use the half-angle formula. So let's recall half-angle formula for cosine is the square root of 1 minus, or is it 1 plus? I believe it's 1 plus. Yeah. cosine of that over 2. Right. So it sounds kind of funny, but it kind of looks so far like we have a radical instead of a radical, so that's good. Now this is going to take place as theta, so let me maybe box this. So this is the half-angle formula that we're using. Maybe I should box it like in red or something. Doesn't really matter, I guess, but that's fine. Okay, so that's our theta value. So if this is theta from the equation, then according to the equation below, then this is equal to, in fact, let me kind of think about this for a second. Yeah, I guess this is okay. So we'll have the square root of 1 plus cosine of this value. And when I say this value, I mean the one that we're halving, which is pi over 2 to the k, and that whole thing over 2. Now this doesn't look quite like what we want, but it's pretty close, honestly. We want that 1 to be a 2, which is actually really easy to do. We'll just multiply top and bottom of the inside of the radical part by 2. So we get 2 plus 2 times cosine of that. But notice, let me kind of do something simultaneously. So we're multiplying top and bottom by 2, so the bottom now inside the radical becomes 4. But notice this result is our nested radical. So this is radical, and it's divided by that. So there's quite a lot to unpack in there. I guess let me, maybe I'll try to squeeze it in. So it's all over 2 to the k minus 1, and then we have the nested radicals of 2's added together. There we go. Okay, so does this really work? Something sounds like it's off. You know what I'm thinking? And maybe I probably should have seen this ahead of time. But I don't, so I knew something was wrong. But it's fine. We're really close. Sorry for the small hiccup here. But notice if you just take the square root of the top, you have 2 plus something, which is involving nested radicals. And this is going to be all over the square root of 4, which is 2. Okay, so what went wrong is that, again, I remember this fact incorrectly. So really it's just this all over 2. So 2 times that. So again, just because this looks a little funny, let me move that note and just write this whole thing over 2. So I think this really is the fact. I just remembered the fact wrong again. But again, I was open about that. It's all going to come together really nicely in the end. So we're assuming that this is true up to some integer k. So now we have that. We still have 2 to the k plus 1 there, so sorry about that. The only thing that's changed is the denominator here is now just 2. Which is really good, actually, because now, notice multiplying it by 2, those will cancel. So really we have 2 plus a nested radical of 2's. But notice we have one more 2 inside this nested radical. So here there were k minus 1 many 2's. And now here, inside of this nested radical, there's one more because of this 2 here that we're adding to the bunch. So this is k many 2's. In other words, one more than the previous amount. Great. So what we have shown is that cosine of pi over 2 to the k plus 1 is equal to this nested radical involving k many 2's all over 2. So that actually proves the induction step of this process. So after the base case, this is called the induction step of the proof by induction. I know I remembered the fact wrong, so that kind of maybe threw things off a bit. But at least we've shown that that fact is indeed true. This fact is true. That cosine of pi over 2 to the k is this nested radical of k minus 1 many 2's, which I'll note here, all over 2. Okay, great. So we've shown that assuming it's true for some value of k, we can show it's true for the next value of k. Now I know there's k minus 1 here, and now here there's k, but that's because k was changing from k to k plus 1, so that means k minus 1 will change to k, because k is kind of incremented by 1. So it's something to think about. If it's your first time seeing induction, this probably isn't the best example for the first example to see with induction, but there we go. So we can say by induction, the fact is true for all values of k. Let me just write that. For all values of k. That symbol just means for all values of k in the set of natural numbers. Fantastic. So now that we have that fact, we're kind of almost done proving what I wanted to prove. But it really has to do with finding the area of the 2 to the k plus 2 gon, that a sub k. So let's now consider, so this is kind of another fact, but let me write this as a theorem now. It's really a corollary of that previous fact, but that's fine, still a theorem. And that's that the area of a 2 to the k plus 2 gon with radius, I guess it's called in radius, I guess it'd be radius still. Maybe it's in radius. But you know what I mean. It's inscribed a circle of radius 1, so the radius of that circle, basically, with radius 1 is 2 to the k times the square root of 2 minus the square root of 2 plus, and so on. So the first step is to split this into triangles. So how many triangles will we have? So this triangle right here is a triangular sector of this 2 to the k plus 2 gon. So in fact, there's k plus 2 many triangles. Okay. Let me think about that for a second. I guess that's okay. Yeah, I guess that's fine. So there's k plus 2 many triangles. So if you had all these triangles and kind of position them so you have a k plus 2 sided polygon, then there we go, that's the polygon we're after. So to find the area of such a polygon, we'll need to find the area of each of these triangles and add those together. But notice this is inscribed in a circle of radius 1, so the side lengths of these are both 1, so in fact they form an isosceles triangle, in fact, each of these triangles. And this angle is actually known. What is this angle? Well, just like we saw, the area or the full rotation of an angle is 360 degrees. We saw when we created a square, the angle was that divided by 4 because there's 4 sides. So in fact, splitting this into k plus 2 many triangles, you'll have 2 pi over k plus 2. Okay, well in fact it's over, let me think about that for a second. It's not over k plus 2. Where it's actually over how many triangles there are, which is 2 to the k plus 2. My mistake. 2 to the k plus 2. Now notice that actually reduces. If you divide top and bottom of this by 2, you get just pi over 2 to the k plus 1. Okay. Also, there's actually a nice fact we can use here, that the area of such a triangle is equal to 1/2 the product of the side lengths multiplied by sine of the angle in between. Okay, how do you prove that fact? There's actually quite a few ways, but maybe we don't actually have to get that far. maybe we can actually look at a kind of smaller fact. Maybe it's a more specific fact. But if we were to take a look at a perpendicular bisector here, which I'll draw in blue, that splits this into two right triangles, right? And notice the area of the entire triangle is the base time, half base times height. So that's a different way of looking at this. So we have a height h, and we have the base, and this is half the base, let's say b over 2. Now, if you call this angle theta, this angle here, call that theta, it's a really, really skinny triangle, right? Notice, theta is just the angle we got, pi over k 2 to the k plus 1, but that halved. Right? So it's really that pi over 2 to the k plus 2. Okay. But more importantly, notice, since the radius is 1, what is sine of theta, what is cosine of theta? Well, sine of theta is just h over, not h over 1, but opposite of hypotenuse, so it's going to be b over 2 over 1, which is just b over 2. And cosine of theta is actually going to be equal to, well, it's going to be equal to the adjacent side over 1, over the hypotenuse 1, which is h over 1, which is just h. So altogether, the area of the triangle is going to be 1/2 base times height. But in fact, half of the base is already b over 2. So this is in fact just sine theta, cosine theta. Really cool. Now in fact, using the double angle formula for sine, and I'm showing a lot of formulas here, but the double angle formula for sine says that sine of 2 theta is equal to 2 times cosine of theta times sine of theta. Let me write it like this, sine theta times cosine theta. So that's a double angle formula for sine. Now this will remind you of that for sure because we have sine and cosine here. But notice we don't have that 2 in front, so this is really half of sine of the angle doubled. And the angle doubled is exactly pi over 2 to the k plus 1. Because like I said, the green theta was half of that angle that we're looking at. So notice we've shown that this is actually in fact true. That the area of that triangle is in fact equal to 1/2 sine of that angle. So that's all I'm trying to establish here. So hopefully I've convinced you of that. And again, I haven't written it here, but I'm trying to start off a proof of showing that fact, which doesn't really seem like we've gotten very far, but we're definitely there because we've split the polygon into k plus 2 many triangles, and now we're finding the area of those triangles. And we just did that. Just did that. So now we know the following, that the area that we're looking for, which I called a sub k, which I know sounds confusing because it's the area of a 2 to the k plus 2 gon. But let's just call it a sub k. Okay. So now we know a sub k is 2 to the k plus 2 times the area of these triangles. And we know now the area of these triangles are 1/2 sine of that angle. Whew, nice. Great. So now what? Well, we're almost there. We're like super close. Almost there. Believe me. Notice, we can cross cancel here a little bit. 2, we can take away a 2 there. That's k plus 1 now. Because of course you had 2 plus, or k plus 2 many 2's. Taking away one of those 2's by dividing by 2, you have k plus 1 many 2's now. For this, I'll use one more, and the last, I promise you, trig identity, which is the half angle formula for sine, which is very similar to the half angle formula for cosine. Cosine, remember, was radical 1 plus cosine over 2. This is 1 minus cosine of theta over 2. And this is the half angle formula, the sine of theta over 2. Let me just make sure I wrote that down correctly. Yeah, I did for the above. Okay, just checking. So let me box this in red like I have for all of the formulas we've been using along the way. So now we're going to write this as sine of pi over 2 to the k over 2. So of course, our theta, as in the half-angle formula for sine in the red box there, is pi over 2 to the k. So notice the area of the triangle is equal to that, 2 to the k plus 1. Perfect. Again, we're almost there, I promise you. Now, this is 1 minus cosine of pi over 2 to the k, because that's the angle that's being halved above, over 2. Multiply top and bottom of the inside of the radical by 2. We get 2 to the k plus 1 times the square root of 2 minus 2 cosine of pi over 2 to the k, all over 4, because we're multiplying top and bottom of the inside of the radical by 2. So the 2 on the bottom becomes 4 now. Okay. Now, the square root of that 4 is 2, so that comes out. And what do we know about cosine of pi over 2 to the k? Well, cosine of pi over 2 to the k is that nested radical of k minus 1 many 2's. Okay. And that, by the way, that was over 2, so maybe I should include that. Let me see if I can squeeze it in here. Over 2, let me try to... Yeah, that doesn't really work out, does it? That's okay. There we go, that works. That's over 2. So these 2's cross cancel. And actually we lose one more 2 there, which loses that plus 1 there. So now we finally have 2 to the k times the square root of 2 minus radical 2 plus all the way to just radical 2. So there we go. Like I said, we weren't that far, and there it is. We're done. So we've definitely proven that fact, that that's the area of that polygon. Now, of course, it's inscribed inside of a circle of radius 1. So as k increases, that polygon area will get closer and closer to the area of the circle, which is circle of radius 1 is just pi itself. So in fact, you can show that, or you can then say, I guess, the limit as k goes to infinity of a sub k is indeed equal to pi. So that's a rigorous proof, or more rigorous proof anyways, opposed to the Pythagorean argument. There we go. Now I wanted to show one last thing, just because I think it's so cool, is let's recall this limit. Limit as x goes to infinity of sine of x over x. Notice that's equal to 1, right? I'm sorry, not infinity. X goes to 0. Losing my mind already. So one way of rewording this is what is known as a small angle approximation for sine of x. So you can say the sine of x is approximately x itself when x is small. Now, of course, small is relative, but you can make it as small as you want, I guess, is what the limit idea says. So in particular, what about when x is equal to pi over 2 to the k? Well, on one hand, sine of pi over 2 to the k is approximately pi over 2 to the k. On the other hand, if you multiply both sides by 2 to the k, then you get this. So that's about pi. Right. Now, this isn't quite where it needs to be like assisting the proof above, but it's very, very close, because notice you can use half-angle formulas to get this in terms of cosine, and cosine itself is a nested radical. So maybe the k here doesn't actually like match exactly what it would need to be. Maybe I should have made it k plus 2 or something like that, and then they'll kind of cancel out like we saw in the proof above. But at least I wanted to show that that kind of relates a little bit. I know it looks kind of weird, but this is kind of one reasoning why that ends up happening. And it's a pretty interesting result. So in fact, this is actually true, that if you take the limit as k goes to infinity, notice the inside of sine will get closer and closer to 0. So sine of pi over 2 to the k is about itself, pi over 2 to the k. So it cancels with that 2 to the k multiplied in front, and you will get pi. So this is a kind of interesting result. Of course, pretty obvious result if you know the small angle approximation for sine. But it's a pretty interesting result nonetheless that I think is, of course, interesting to take a look at. But what's weird is that it is kind of self-referenced to pi. So I don't know how useful it is in approximating pi, because you kind of have to know pi in order to figure out what pi is. Not super useful. But the nested radical one I think is definitely a treat to see. So if you want to see more videos like this one, please share this video, maybe comment, like, and subscribe, all that fun stuff. And I'll see you in future videos. Thanks for watching, and I plan on making more, but we'll see how this goes. If it gets as much traction as I'd like, then we'll definitely see more videos like this in the future. Thanks for watching, and I'll see you in the next one.